Hi, thanks for watching. And today I would like to talk to you about the most basic unit in analysis, which is the set of natural numbers, which you probably learned of it as being the set of 1, 2, 3, etc., etc. So that's probably the definition you've been ingrained, but if you think about this, it doesn't really tell you anything about what the natural numbers are. In particular, what makes n so different from the integers or the real numbers? Well, there are two properties that sets n apart from other sets, which are as follows. First of all, n has a least element. N has the smallest element. Element called 1. So if you draw it on an axis, this is n, and basically it starts with 1. It's the smallest element, but of course had other elements like 2, 3, etc., etc. And this is very different from the integers. So if the integers have no smallest element, if I give you a number in z, you can always give me a smallest number. If I say 42, you'll probably be like 41. If I say minus 30, you'll probably be like minus 31. So that's different. And moreover, also kind of slightly different. In other words, every number n has what's called a successor, which is called n plus 1. Every n in n has a successor n plus 1 in n. In other words, every number has a number that comes after it. So the successor of 2 is 3, if the successor is 42 is 43, etc., etc. And this is very different from the real numbers. In other words, there's no number that really comes after 2, so no real number, because you could say 2.5, but you could also say 2.25 or something. So this is very unique about the natural numbers. It has a smallest element, and every natural number has a successor. But this still doesn't tell us how to define n. So those are two nice properties n has, but there are other number systems with that property. And so in the second segment, we will define the natural numbers. I would like to mention that you can define them explicitly. And in fact, if you're a student in my class, there's this amazing homework problem where you construct the natural numbers. But in case you're just a viewer, I still appreciate you, but let me just briefly mention how to construct the natural numbers. You define 0 as being the empty set, and given a natural number n, you define n plus 1 as being n union the set containing n. And that way you can define natural numbers. But in this course, what we'll do, we'll take an axiomatic approach. What is an axiom? It's just a set of rules, and math is just playing games with those rules, more or less. And because the axioms are so instrumental to our knowledge of math, we'll call it the Peano axioms. So let me now tell you about the axioms of natural numbers. So how would we define the natural numbers? In other words, Peano's axiom says as follows. There is some magical set called n. So there is a set. Set n such that the following holds. Couple of things. First of all, the number 1 is an n. That's one thing. And moreover, it's, the successor business. Namely, if n is in the set n, so if a number n is in n, then its successor is in n. So in other words, if an integer n is in it, then the successor n plus 1 is in it. And so in other words, you can always go forward, but very important for the number 1, you cannot go backwards. So 1, so the primal element, if you want, is not the successor of anything. The successor of any element. In the set of natural numbers. Again, you could say, well, it's a successor of 0, but we assume 0 is not in n. So there's nothing that precedes 1. That's one thing, but again, technically we haven't shown that there's something that precedes, n, for instance. We don't know that. And moreover, it's something that should seem kind of obvious, but if you start with different numbers, the successor should be different. So if n is not n, then the successors are also different. N plus 1 is not equal to n plus 1. And last but not least, there's something called the induction axiom, which I'll announce very soon. Okay, so those 5 axioms consist of Peano's axioms, and we just assume they're true. So it's something you cannot prove or disprove, but I hope that at least those axioms are more or less obvious. So I think it should be obvious that if a number is in it, then the successor is in it as well. And the nice thing is, again, using those axioms, we can define numbers like 2 or 3. So for instance, 2 is defined as just the successor of 1, 3 is defined the successor of 3, 4 is defined as a 3 is defined as a successor of 2, 4 is defined as a successor of 3, etc., etc. And the question is, and that's quite interesting, because I told you that now we can define 2, we can define 3, and successor business, we can define 4, etc., etc. But the question is, can we really define all the natural numbers that way? Is it possible to reach all the natural numbers by just taking successors? It turns out the answer is yes, and that is what this last axiom is saying. And this last axiom is what I call the induction axiom, because it's really the basis of the principle of mathematical induction. So, 5, induction axiom. And again, I'll talk about induction in the next video if you're interested. I hope you're interested. If you're my student, you have to watch this, okay? So, and what is this saying? Suppose you have a set S. If S is a subset of N, such that 2 things. First of all, 1 is in S. So 1 is in S, and moreover, whenever a number is in S, then its successor is in S. So if N is in S, then N plus 1 is in S. Again, just like the situation we talked a couple of minutes ago. 1 is in S, therefore 2 is in S, therefore 3 is in S, etc., etc. Well, what the induction axiom says is that S is really all of the natural numbers. So then S equals N. In other words, if we successively take successors, so if you take successors over and over again, then indeed we reach all the natural numbers. In other words, we do not skip any integers by doing this process of taking successors. And hopefully you're like, okay, this is obvious, and it should be obvious because it's an axiom, but again, the idea is it's certainly possible that if you take a successor going from n to n plus 1, in theory what this axiom is saying, it's in theory possible that you skip an integer in some sense. But this axiom is saying, no, this is not true. You're not skipping any integers in that sense. You're really reaching all of them. And again, very important, this is very wrong for the real numbers. So you could have 1 being a real number, and you could go from 2 to 3, but you can skip a lot of real numbers in between. And in fact, you do like 2.5 or square root of 2 or 2.5 square root of 2 plus 1, pi over 2 plus 1, etc., etc. All right. And again, in the next video, I'll show why it's called the induction axiom. But now, in order to tell you sort of what a typical math proof is like, let me prove the 5th axiom. And I'm being very sarcastic because it's not a proof. You cannot prove an axiom, but again, it's just to give you a flavor of how our actual proofs later on will work. So again, just to give you a taste of analysis proofs. So, proof of 5. Okay. So suppose it is false. So suppose 5 is false. What is this saying? That is, there is a subset of n such that first of all, 1 is in S, and whenever n is in S, then its successor is in S. So suppose there is such a set with the 2 nice properties, but that set is not all of the natural numbers. So, in other words, there's a strict subset satisfying those 2 properties. What does that say? Again, in terms of pictures. There's a set such that 1 is in it, then 2 is in it, 3 is in it, etc., etc., but at some point it kind of stops. Okay? So at some point there is some element that is not in S. And well, there might be other elements as well. So you could have this one being in S, and then suddenly elements not being in S and reappearing and reappearing. Okay. And this is natural numbers, and everything that's in blue is in S. Everything that's in red is not in S. Now, as I said, S is not all of n, so in particular there are elements in n that are not in S. So there are some red dots here. Let n naught be the first red dot you see. So you see blue, 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 and then suddenly a red dot. So in other words, let n naught be the first, or if you want, the smallest integer that is not in S. First, or if you want, smallest, again, positive integer not in S. Again, think of it as follows. You first go through the elements in S, and the first one you see that's not in it, you call it N naught. Okay, so first of all, could N naught be 1? Well, strictly speaking, no. So N naught is first of all strictly greater than 1. Why? Because the argument is very easy. 1 is in S, but N naught is not in S. So how can they be the same thing? Because 1 is in S. Again, that's by assumption. So the first assumption says 1 is in S, but N naught is not in S. Because that's by definition of N naught. It's the first integer not in S. So how can they both be the same? You can't, unfortunately in math you can't multi-track drift. Yes, okay, so that's why you can't be in a set and also be not in a set. It's not Schrödinger's cat or something. So that's why N naught is not 1. Okay, so definitely it's greater than 1. And here's the interesting thing. Remember, N naught is the first number that's not in S. In particular, everything before is in S. In particular, if you take N naught minus 1, it is in S. But here's the upshot. If you take N naught minus 1, it is in S. Why? Because everything that precedes N naught is in S. Because remember, we assumed N naught is the first element that is not in S. It's the smallest one. So if this is not in S, it would be a new and smaller candidate of an element that's not in S. And that contradicts the property of N naught being the smallest one. Okay, but then what do we have? That's quite interesting. We have N naught minus 1 is an element in S. But remember, whenever you take a successor of an element in S, you still get an element in S. So, but then, if you take N naught minus 1 plus 1, that's in S. So if you add 1 to this element, it's a new element in S, but that's nothing other than N naught. So in other words, N naught in the end, it's not a red element, it's a blue element. But again, this contradicts the fact that N naught is an integer not in S. So this is actually a juicy contradiction. A contradiction with what? A contradiction with the fact that S is not all of N. So indeed, it is true that S is all of N. S is all of N. Well, ironic proof. Okay. I know it looks like a legit proof, but let me tell you why it is not. So, because of two reasons. Because, so first of all, what does N naught minus 1 even mean? We know that every number has a successor. That's not a problem. But how do we know that every number except for 1 has a predecessor? So how do we know that there's a number that precedes N naught minus 1? Remember, we haven't really defined numbers yet other than the axioms. And so, in fact, we don't know. We cannot always prove this. So that's one issue. The other one that's actually way more important is, even if we have a predecessor in all this business, and even if we have a number that's not in S, how do we know that there's a smallest number not in S? So, I agree. Again, I agree with you that there's numbers not in S. But how did we know that there's a smaller one? Of course, in this picture, it's obvious because we have integers. But what if you have a scenario that there's a continuum of numbers that are not in S? How would you know there's a smallest one? I mean, let's say you choose 2.5. Maybe you can choose 2.2. Maybe you can choose 2.1. It's not clear that there is such a smallest number, and this is extremely important. You'll see in a couple of sections where we'll talk about least upper bounds and greatest lower bounds. So, as I said, unfortunately, this fifth property, you still have to take it as an axiom. You cannot prove that axiom so far. All right, I hope you like this. If you want to see more math, please make sure to subscribe to my channel. Thank you very much.